And welcome everyone to this week's Wednesday webinar. I'm Shannon Dillon with University of Maryland Extension. And our speaker today is Jared Miller with University of Delaware. And I'll have Jared, you should be able to pull up your slides.
Yep. Got it.
Great, thank you.
Thanks everybody for having me on today or visiting with us. Jared Miller, Extension Agronomist with University of Delaware, and working on our Carville Research and Education Center. Going to give a short lecture on precision ag hardware and equipment, some of the stuff that we use here in Delaware, and just an overview of the kind of equipment and things that's helpful to understand if you're going to discuss things with farmers, other ag service providers. Being familiar with the equipment, this lecture will not make you an expert in absolutely any of it, but at least will get you used to some of the terminology. And one of the first things we have to start with when discussing precision ag equipment are global positioning systems, which are one of the without it, we can't have precision ag, because we have to precisely know where we are in the field to do any of the kind of work we want to do, including variable rate application or mapping of field qualities, anything like that with EC. So GPS, global positioning systems, came out because of having satellites. And to mark a point on the ground and have elevation, you need at least 4 satellites. The more satellites you have, the better your accuracy is. So you can see all these circles. We can measure the distance. We know where the satellite's at as best we can. And you know the distance of that satellite to the ping it sends to the ground. And if you have 4 satellites, where they cross tells you where your point is at. So 3 will get you XY, get your latitude and longitude. 4 will at least get you your elevation as well, which is very important in determining some of our soil characteristics. So once we had GPS up there, we could start to get accuracy. So you need more than 4. Definitely most of the time you can get 8 to 12 on any given day in any location and get your accuracy out there. 20 years ago, they used to, the military had a way to, they scrambled the signal a little more, so it wasn't as accurate. It still can be a couple feet off. We'll talk about how we correct that than it used to be. But I remember having the handheld units back in the late 90s that were not very accurate compared to today, like what you can use within your car or anything else. So GPS receivers are going to be positioned, can be on your equipment. You see we have one here on our EC, our Veris EC meter, but certainly has to be on the tractor at least, have GPS equipment. So by having any kind of receiver, this is what's actually talking to the satellite back here. This red dot here, right here, that's going to be the receiver on top of your tractor in this case, or it can be on your backpack if you're walking through the field. So you need the receiver to know your location that's going to be able to talk to all this equipment. So without GPS, we don't have precision ag because we don't know precisely where we are in the field. So they're very integral with the spread of precision ag. Once we had this, and once people realized this technology existed and what they could do, that's when we started coming up with the kind of equipment that we could use. So they're going to be the most common piece of precision ag equipment on farms. Almost everybody's going to have one. If you buy new equipment, it probably comes with some sort of receiver, and possibly when we talk about auto steer and things like that, that would be combined with it. So precise location is necessary for precision ag. Otherwise, we can't map this landscape variability that we're looking at. But it still is not going to know exactly where you're at. Even with those satellites, there's still an error in the field. So it's one thing if you're driving your car down the road and it knows that you're supposed to be on the road, so it keeps you there when you're driving through Google Maps or anything like that. It's another if when you cross this boundary, you see all these different fields we have here marked. If you're going to turn seeding rates on or off, if you're going to apply different amounts of fertilizers, pesticides, you're not going to be accurate if you're 10 to 20 feet off in that case. It needs to know exactly where you are at. And that's where we get into a differential corrections. So a differential correction is going to have a base station or some way to know exactly where itself is at. And then it's going to look at your relative location and try to correct that signal. So the satellite's going to say, well, this is where I think it's at. Then the satellite's going to be able to talk to, in this case, this is our research farm. We have a base station that we know exactly where the base station is at. So by talking to both of these, it can send a correction signal to the tractor, or if you're walking the field with a handheld unit, and correct that and make sure it knows exactly where you're at. And we're going from feet down to, in this case, 1 centimeter accuracy. So that kind of accuracy depends on what you want to do. It's one thing if you're mapping a field, say a yield monitor, you can probably be a couple feet off and it's going to be good enough. If you're trying to precisely put down nutrients, tile drains, anything along those lines, that's when you want to start to have 1 centimeter accuracy. If you're doing drone mapping, if you're mapping fields with a drone, if you're going to have multiple maps over a season, you're going to want to make sure that you have the kind of accuracy with that RTK has, this differential connection, real-time kinematic. It's one of the best known versions of a correction you can have. So you know exactly where you're standing and that you can repeat these things every year. You want these maps to overlie. There's one part about precision agriculture, it's collecting data temporally, not just spatially, but over time, having maps of these fields year after year of what your application rates were, what your yields were, and you want them to overlay so you can make these determinations. So the more accurate they are, the better it is. So one of the earliest and easiest things that we could have in terms of accuracy in equipment would have been the use of a light bar. Light bars are not as common now because we've replaced them with auto steer, but a light bar would be talking to that GPS unit and know where you are in the field. And if you get too far on or off the path of where you want to be in that field, it could tell you that you want to move back into the field to the left. You want to move back to the right and keep you in line as best it could. So in this case, you have to watch this monitor and you have to keep yourself in line. There's no auto steer involved here. We still have these around at our station, and we just put one on a four-wheeler because we want to use the four-wheeler to map a field with a piece of equipment we have. Now, farmers aren't, some might still have these tractors, but a lot of tractors come with the auto steer at this point. You don't necessarily need this. So it's easily adoptable. It's the reason so many people could use it. It's easy to understand. You're using lights, you have a GPS unit, it tells you where you want to be. You do have to do some programming. You need the receiver, the differential correction. You need a computer that can talk to it, which is this, probably inside of it, and then the light bar display. So you didn't need much, and it's easy to understand. So it was easy for people to adopt, and it doesn't steer, but at least it helps you keep your place in the field and know where you want to be. So in this case, the way a light bar would work is first thing you'd have to do is you'd have to define an AB line. You'd have to tell it this is the line, because it has to know where you're at. It doesn't know where you're at in the field. It doesn't know the size of the field. It doesn't know how far apart you want these passes to be. So you define what they call an AB line. So it's a reference line for guidance. And then you have to tell it, I want all my passes to be 90 feet apart. So when you turn here, that's when those lights are going to kick in and tell you whether you're too far to the left or too far to the right. So you have to make decisions. It's not a tool you just put on there without understanding some things about your field or what kind of management you're doing. If you're applying a fertilizer, if you're planting and you want to keep in line, you have to know how far apart your passes are going to be. And then it helps you keep in line. So you're defining that pass distance. And then your computer, that's why you need a computer. It helps determine where those other passes should be. And the light bar keeps you on the pass. So this is a very simple map of a field and has square edges and doesn't have any of the variability you might have in circular fields or odd patterns. So a major advantage of a light bar and why so many people adopted these, it can be placed in any equipment. That's what we're putting one on a four-wheeler. You can put one on small equipment or large equipment. And it can be placed directly over the steering wheel where you can see it. It's right in front of you as you're driving. So you see those lights and line up. But the reason you can adopt these so quickly is it reduces application errors from overlaps and skips. If you've ever used equipment like I did as a kid back in the 80s and 90s, you would have a bar going out across this tractor with maybe chains, and you might have to look at where your passes were to keep in line. It was very easy to overlap. You might have foam markers that dropped foam along there, and people still use these to a degree. But with a light bar, it would tell you, you need to go over to the left or right. So it reduces operator fatigue and it reduces error, and it's easy to use. So they were very easy tools for people to adopt. And it was great in poor visibility. So what would happen at night in this field when it gets dark? Well, you might start missing your passes. But now with that light bar, it's talking to a satellite as long as you have a good signal. Now you can drive across this field in poor conditions, poor lighting conditions where you couldn't see. So reduces fatigue from the operator from having to figure out where he's at, she's at, and then also allows you to work longer hours, but at least get it done on a good weather day. You've got good weather and you want to work through the night as a farmer, you can make those decisions. So it's definitely a big advantage to having a light bar in that case. So they had other features. Return to point, you could tell it to mark a spot in the field and bring you back to that point. Snap to path, find the closest next path and direct the driver there as you're making those turns in the field. They could come up with contour following for fields with irregular edges and curves, and then data logging, recording positions, what you need for a computer. The light bars are one of the or piece of equipment when they track precision ag equipment that over time people have abandoned. But what they find is they've abandoned these and then moved into assisted steering or auto steer, which is more of some of the things we think about now. When we think about precision ag equipment or self-driving tractors or some kind of assistance. So auto steer, one of the first versions that you can see right here, you see this little just turning wheel. It again needs that GPS. It needs a receiver. It needs satellite data to tell where it's in the field, and you need to mark where you want to be. But very simply, this wheel would turn and turn the wheel for you. Now, most tractors that are newer that you're going to buy now, they're going to have integrated equipment down underneath that's going to steer the whole tractor. You're not going to have this big lumpy thing on top, but you could adopt any tractor easily to help you steer with this bar and this little foam patch to steer the wheel for you by mounting it here and then connecting it to a computer and a receiver. So development of this actually began in the mid-90s. So again, once we have GPS, once we have the satellite data, then people that are thinking are like, well, what can we do with this for ag? What can we do? And one of the first things was actually to fly planes using some of this work. So NASA and Stanford worked on RTK, landed airplanes with it. They created a company that branched into ag applications, and they released auto steer in '99. So it's been around for over 20 years at this point. So this is, you can see a clear picture here of how you can mount this on any tractor. You could do it now. Yes, you could put it on a little Kubota, I guess, if you wanted to. Mount a controller or integrate it. You need that GPS antenna on the roof because it needs to have coordinates. You can also look at roll, pitch, and yaw, which is how you might move side to side on a hill, because if your tractor turns a little bit to the side on the hill and your GPS is on the top, then your position is incorrect with ground level. If it thinks you're over here when you're here. So it can also look at roll, pitch, and yaw of the whole thing and help make these corrections. You also need that base station transmitter and probably a touchscreen display. So it had a bunch of parts, but it was still fairly easy to understand what you were doing. So with this, the same thing. This is our auto steer in our research tractors. Here's that AB. When you set an AB line, so when we go to any of our fields, that's one of the first things we do if we already haven't set it on our research fields, is set this AB line and tell it, this is the straight line path I'm going to be following back and forth on, and then how far apart your passes are going to be based on the equipment that you have. So just like a light bar, the benefits of auto guidance come a lot down to that visibility and fatigue. So for the most part, it's a base model component. Its costs that come down. So more than likely, anybody buying new equipment, you pretty much expect it to have auto guidance. Now, this isn't self-driving. You're still going to sit in there. You're going to correct it. You might not like how it turns on your end rows or anything like that in the field. So you might have to do some corrections and work with it. But for the most part, when you're driving down that straight, you can turn around and look at your equipment. You can make sure things are planting right. You can check other monitors. You can, I guess, watch TV. But for the most part, it's going to reduce stress and operator fatigue that way. If you've ever planted without it, you know how much you have to watch your lines, turn around and watch your equipment, make sure everything is working. It takes one thing off your mind. Still think about it, but it reduces some of that fatigue. So you can watch other monitors, and because you're not concentrating on staying straight and following those rows. So less skips and overlaps are going to save money. So you don't overplant your rows. you don't over apply fertilizer or pesticides. You also don't underapply. So you can also cause issues if you miss. Herbicide overlap can damage crops. Herbicide gaps can damage crops because then you have weeds take over. So there's a lot of benefits to this that make it easy to adopt and easy for farmers to understand. There's a lot of technology that it's hard to figure out what am I going to get from it. But auto steer, Lightbars, those were easy to adopt because you could immediately feel how it took a weight off of you inside the equipment in terms of monitoring all that stuff at once. One of the other early adopted pieces of equipment would have been a yield monitor. This is one that didn't necessarily need GPS. People were doing different things to do yield monitors before we even had satellite data because it's anybody, whether you're a farmer or a research scientist, you know there's field variability. And so the yield you get out of a field is going to be the good parts and the bad parts. Well, can we map an entire field to figure out, can we correct things or where's everything going on in this field that we need to understand? So Ag Leader released one of the first models in '92, and it didn't necessarily need GPS. You could add it, but it didn't need it. So this is one of the oldest and most adopted pieces of precision ag technology. Same thing, if you buy a combine now that doesn't have a yield monitor, I don't know where you would get that from unless it was used. But if you buy something new, it's going to come with some kind of yield monitor because you can immediately see the value when you're driving across that field to see the yield as you pull it out. So it should be considered standard at any new combine. Our more modern ones, of course, are going to work with tablets and monitors with inside the tractor where you're going to map yield visually. So this one, you can see it. You can see what's happening in your field. You can see your moisture content, the bushels that are going across there. You have to enter some data in there to figure it out. In this case, if you have everything calibrated right, it's producing a map as you go across the field. How correct that map is, how accurate it is up to the farmer, but you can see our high yielding and low yielding along the woods here. This is our research farm. This is where I have most of these maps from. But as you're going across there, you can see the range of yields that we have here, 130 bushels to 230. So now you can see this value. Of course, there's lots of squares here because it's research plots versus field contour stuff. You can see where we have a drown out probably in this area. But this is another immediate thing like a light monitor that's very easy for farmers to understand. Even if you never use the data to make any kind of analysis or changes, you can see what's going on in the field. So the immediate value to something like a yield monitor, particularly with our use of tablets and apps and software that are much easier for farmers to use than they used to be. So again, we needed GPS first. Once we had GPS, people could start to think, can I use it to map yield? Not just map where I can put products down, but map what I'm pulling out of this field, map different parts of it. So it's very similar to a light bar, an immediate visual representation, and there are grain, cotton, and even sugarcane versions. But of course, up here in Delaware, I deal with grain. I don't know much about the other versions of yield monitors. Here's another one that you can see the soil type here. And I know this because we run research projects out here all the time. Deer damage and poor soil along these edges shows up year after year, but you can average those out. It's a great thing about having yield data. You can start to figure out during different climates, during different climatic events, whether you have lots of rainfall or droughty years, what's the average representation of yield across this field. So again, they're going to have this in-cab display. They're going to have differential correction, but then you have a lot of sensors involved within a yield monitor that has to be within that combine. It starts to get more complex. There starts to be more parts. When you have more parts, more things break and things can go wrong in terms of the calibration. So you have to have a mass flow sensor. You have to know your grain moisture. It has to know the elevator speed, the cutting comb height, how fast is your harvester driving, and of course, GPS, the harvester location. So with this, it's not like a light bar, which has a little bit of equipment. You have to add a lot of things to this combine. And so you have to figure out how we're going to measure yield as we're going across the field. And one of the most common is of a mass flow sensor is an impact plate. So you have a grain elevator in the combine, and it's pretty much taking this grain and throwing it. I think I have a picture. Maybe I got rid of it. And throwing it at an impact plate that's measuring the force. So that's why you need to know how fast is this moving? What's the moisture content of this material? And you have to actually understand what kind of yields would cause an impact on here, and how do you correlate that to yield? So the sensor measures the force from grain being thrown from the elevator. Force is mass times acceleration. So that's how you get, yeah, again, I thought you wouldn't ever use, this was from a class I was teaching undergraduates. You think you're not going to use physics, and then this information comes up. It's always out there somewhere. You can't escape the sciences. All of them are involved in our lives every day in some way. So force equals mass times acceleration. So this is how they can figure out yield. And the sensor on the elevator is going to measure your speed. So that's your acceleration right there. The problem with yield monitors is you have to calibrate them, because over the season, as the moisture content of your corn dries down, the calibration is incorrect. Old monitors might only use, you might use two. Okay, well, I got a low and a high, but the problem is the way these sensors work, they're not going to be necessarily a linear path. You're going to end up needing, in most cases, this is from University of Nebraska Extension, four different points. And you're going to have to do that at different points over the season. And if you've worked with enough farmers, you know, when you want to go, you want to go. So some of the ways they do this, they can slow down, they can speed up, they can go to low and high flow, they can go into different parts of the field where they know it's high or low. But if you want to have accurate data, you need to calibrate your sensors. So sometimes when I see massive year-long projects that look at satellite data versus yields that they've gathered from farmers, you always have to wonder, how accurate is this information? So if you just want to map a relative differences, calibration probably is not as big of a deal. If you want to know that it was 200 bushels here and 150 there, you need to calibrate, and you need to calibrate at least 2 times in the season. If it takes you the entire month of September to harvest your fields, you want to have multiple calibrations. So it's a problem with the accuracy of this data if we're not aware of how much they've been calibrated. There are other grain volume sensors. If you hear about them, if you work with other people, not used as often that I know of, a photoelectric sensor, gamma rays, paddle wheel grain sensor flow, different equipment, but the most common is going to be the impact plate. Some other sensors we can add to combines, not as big in the US yet. I have seen them used more in Australia because they might grow more small grains, are protein content and oil content. And what's interesting about these sensors is we're looking at quality and not just quantity in this case. So it might work here in Delmarva. We have malting barley facilities. So being able to measure the protein content of malting barley as we're going across the field and having a map of that gives us soil quality. And that is going to be a reflection of soil conditions and soil nitrogen availability. So this is another map we could possibly have. It's not common that I know of in our combines in this region. I do see them using it towards Australia. I see it come out there more often. So, but we do have canola here. We consider soybean. Of course, our soybeans here go to poultry, but oil content, and they use near infrared spectroscopy. So you could see this more often in our region in the future. So after you get out of combines, you have to start talking about planter parts. This is when everything gets more optional. Light bars were common. Auto steer is probably common. A yield monitor is going to be pretty common. Everyone has it, not necessarily because they wanted it, sometimes because it came with the equipment. Planters, there's always new parts. I can't keep up with this. I'm not an engineer. I do what I can, and that's our engineer back here at University of Delaware, James Adkins, putting this planter together. He always knows all the parts. He knows the newest equipment, and that's how we try to keep up with it. But for the most part, he's updated our planter with these. You don't need them, though. You don't have to do it. It helps. But this is where you get to things that are optional with farms. So while yield monitors have been around, planters for planter parts are being added, and they're updated, and they're always trying to come up with new ideas. And you'll see one of them in here. But we've had these around for a while, too. I grew up with this one. I didn't know what it was when I was a kid, but we had this. These 6-row planter with 6 lights that are monitoring your seeding rate. I don't know how it did it because I was a kid, but I remember using these. So they're looking at seed flow, watching for skips and doubles. So again, it's helping you know if the planter is working without getting out and stopping and looking. So we've had planter monitors, but what we're including now is GPS and more advanced monitors that have computers in there that are looking. So you can see here, it's telling you your population, It's telling you your singulation, your spacing quality, 95% spacing quality. So we're adding all this data in here: population, singulation, your downforce pressure, all these things on these monitors. It's reading out of a planner that's going to tell you how well you did. So you can see where you might have had an issue in the field with lower and then higher populations, and maybe you can correlate that back to yield later. But it's ways to improve. So here's your planner performance as you go across this field here. How well were you doing in your singulation? And it can monitor this by each of these row units. It can figure out how well they're doing. You can see when there was an error, maybe stop and fix it. So if you're not familiar with a planner, they call this whole thing a row unit. So your seed would go in here. These are holding fertilizer, maybe herbicide, but this is usually our starter fertilizer up in here. So here's your row unit. Your seed's going to come down through here, and here's where you start adding all this equipment. So one of the first ones we can talk about is a seed meter underneath here. And this one is on our planner called Sure Drive from Ag Leader. So you see Ag Leader, again, been around for a while, always coming up with new ideas. So our modern one is going to use electric drives instead of chains. We certainly still use chains on some of ours. They take a little longer. It's a small electric motor on the row unit, so it helps control the rate of seeding with more accuracy. Because if you've ever planted a crop, you want that spacing perfect, because you want them to access nutrients and water but not compete with each other. So if you get one that's too close, you're going to lower yield. And if this is too close, more than likely it missed that one, and then you have a gap. So we really want to improve on that as much as we can. If you get that spacing correct, you're going to maximize yield across those regions. And that's what a lot of this equipment tries to do. So you can have individual row control. You could shut off a row. And we've done that. You'll see some farms, if you look at aerial imagery, let's say they've got a 6-row planter and they come up on an end row that's running like this, and you can actually control it, and it will stop each one individually based on where it knows it was already planted. So that's what you can turn these off. So you can shut off rows and reduce overlap. Well, now we're not only keeping our singulation right, we're not doubling up on crossing rows, and you don't end up with overpopulation. So you don't plant too much seed and you don't have competing seeds. So that's what we start to call section control. So you can attach these to different meters. So it's going to have to, again, it's going to need a monitor. It's going to need GPS. It's going to need to know where you are in the field. It's going to need to know how many rows you had on the planter. It's going to need to know how far back the planter is on there. It's going to need to know how wide the planter is. It needs all kinds of information from the farmer, from who's ever running the equipment, to know where it's at so it can shut some of this off. But then it's going to record this data as you cross the field. Here's our rows: 1, 2, 3, 4, 5, 6 rows. We have a small planter. It's a research plan, but we had some skips right in here on 1 and 6, and then you can see where we had some doubles here on 3 and 6 you call across the field. So it's recording that data and recording a map for you. So it's going to speak with the planner control module on the display and record all that information. So this is what we call swath control. It works the same when we're going to talk about sprayers. So you can see as a farmer gets across this field that it keeps planting here, but it stops planting there. So it shuts off sections of the equipment. Not everybody has this. You don't have to have it. You don't have to have individual row control. No matter what, you can shut it off. At least you can keep track of things. But if you're going to have these units on each row, you might as well have it do something like that. So a planner would have these different row units you can shut off. So it needs GPS. Here's the GPS on the tractor, but you're going to have to tell it how far back the planter is, how wide the planter is, and it's going to have a map of where you already planted. So all that's not hard to do, but those are considerations. It's not just plug and play. You have to have a bit of knowledge to run this equipment. We also have seed sensors that are going to give you accurate control, accurate counts. So besides the seed meter that's trying to control the flow, we can count the seeds to also be sure that that's what it's doing. So here we can have a strobe light that's passing a signal along there. So it's going to be able to count these seeds as they cut off the lighting. So the seed passes through the light, breaks the beam, and allows for an accurate count. Relay it back to the monitor. So we're tracking, we're making a map. It's not doing anything. It's just tracking what our planting is. This is a newer piece of equipment, very specific from Precision Planting, called a smart firmer. And this is your furrow that's running along the furrow. So this one is actually gathering additional data using electromagnetic spectrum. So it's measuring soil moisture and temperature. It's going to measure residue and organic matter. So it's making a map of the field. It's given a map that might give you a more accurate idea of why something was high or low, because if we're already passing across the field with a planner, why not gather more data? We have not used one of these. I've seen good results from the University of Georgia. They were pretty interesting. We haven't added them yet because we have to consider costs and whether it's beneficial or a farmer would adopt it. We have added downforce to our planner. So as you're going across a field, you got to get the right seeding depth. If you plant too deep, it's going to struggle getting out of the soil. If you plant too shallow, it could have possibly anything from slug damage to possibly not enough moisture if you have a drier soil at the surface. So downforce helps keep your seed depth correct. So we've used downforce for a while. We have springs, but what we can use now using hydraulics and with automatic downforce is as we go across the field and there are different conditions, it can respond to it and change. Instead of just having one downforce, as you go across different soil types, might plant too deep here and too shallow there, you can have it adjust itself. So we do have this automatic downforce. I can tell you in Delaware, we haven't noticed a lot of difference with downforce across our soil types, but it certainly has benefited people across the country, depending on what kind of soil they have. At Delaware, our sandy soils, even when it gets into clay, we haven't noticed as big of a difference. You can also have starter fertilizer control. So here you can see all these modules that can go on here. We've got the planter control module, liquid swath control, rate controls, because besides controlling the seeding rate, you can control your starter fertilizer rate. If you know you have a poor or better part of the soil, if you know you want to, we have research projects, so that's what we use it for. If we want to go across the field and change our nitrogen rate so that we can have a better idea of what the starter should be, that's what we use it for. But you can have individual control about what nutrients you're putting out and how much. If you think you need less or more starter across the field, you can vary that within and on a planner. Of course, you also have larger equipment for applying fertilizers and herbicides. You can have a liquid sprayer. We can have a dry spreader, and we can also, same thing, here's your GPS unit on top of here. This is going to be pulled and use the GPS on there to mark with. But you can do variable rate controls on this equipment as well, whether it's liquid or broadcast. And again, that'll be based on whether you know you want more or less of a certain amount. So you can see as we're stepping up, we start off with GPS and light bars and driving tractors, easy. When you get into this kind of material, when you get in this kind of technology, it's decision making. So it's not just plug and play at this point. Well, why do you want higher or lower rates of a fertilizer, of an herbicide? You have to know something about the field that you're responding to. And this is when we get into variable rate application. This stuff is more difficult. It's not necessarily adopted by everybody because you have to understand what you want to do and you have to get good advice on how to do it. And we're still figuring some of that stuff out. So we've always had sprayer rate controllers. Here's an older one from Raven, 1980s, boom and flow controls, because we want to have accurate herbicide applications anyway. We want to accurately put out the rate we need, whether it's variable rate or not. We need to make sure that we're putting out the right rates. But when you add in GPS in the 90s, now you can make a map of your application rates, or if you know you want to put more, particularly fertilizer is one of the easier ones to think about, more or less fertilizer across the field, then you can start to vary that rate. And this is a project we did. It's a variable rate liquid application of fertilizer to a small grains crop, where they can do both with their sprayer. They want to test a straight 30-pound rate of nitrogen. They test a straight 30-pound rate. They used a drone map that we made to figure out a variable rate based on the crop response. So if you've ever seen a green seeker or using NDVI on a tractor to make these same kind of things, reading how well the crop is doing and applying a variable rate. So, but you need equipment that can apply a variable sprayer rate to do something like this. So this isn't adopted as easily because you have to deal with equipment. You have to deal with a variety of parts and sensors that might break down that you have to understand, but you also have to go to make these decisions. And that's what this project was about. Is a flat rate better than variable rate as we go across this field? But you have to map it. You have to decide what's high and low. You have to understand how to use the equipment. And so it's the learning curve with this stuff goes up higher and steeper. The great thing about it, one thing that you can do without thinking would be that swath control again. So one of the benefits of having it without thinking about what you're applying is that it simply knows to shut this boom off, to shut the boom off here when it crosses where it shouldn't be. So you can see with these sprayers, because we have all these nozzles, you got a nozzle spread across here and these spots across here, that you can have a tighter, a less overlap versus granular. When you're spreading something wide, you're just going to have more crossover. So you need to have, you can have swath control. So this is more straightforward versus this map here where you have to make decisions. Here, you are saying, well, I'm going to spray the same rate, just shut it off when I've already passed something over. And that is something that works really well. So on your sprayer broom for liquid applications, they can be separated into nozzle control. You can turn off individual nozzles, but for the most part, what people probably have is section control. When you fold out these arms, maybe it shuts off this section if it overlaps. So you get a little bit of overlap here, maybe if you're hitting a row, but you turn off sections. You can do individual nozzle control, but it is more likely to say, it's easier probably for the equipment just to say, shut off this part of it, shut off this part, and just spray in the center. So each section, well, this is getting to engineering, would have its own solenoid. You can have individual nozzle control if you want it. This is another engineering slide from discussing with our engineer, because there are other things it has to think about. You see where it gets more complicated again, and I'm an agronomist, not an engineer, but some of the things they have to think about is as you're turning these corners, because of differences in, you can easily over apply here, maybe differences in pressure across the region. This is that variable nozzle pulse that makes sure as you're turning corners, you're going to have an even rate applied, something that we couldn't do without this kind of technology, because it knows to work and make these adjustments. So these are the kind of things that improve economics and environmentally if you consider over applying here versus under applying in this region if you're using an herbicide. So again, here's your sprayer boom sections. Here's some University of Nebraska extension course out in the Midwest. They used it longer than us and have lots of great documents about precision ag. So these boom sections are going to automatically turn off. So you see a little bit here, most here. So there's some overlap, but you're really reducing it, where before, to be sure, the farmer would have ended up spraying this whole area. And then as you come back across the field, same thing, it ramps it up and slowly starts spreading out the amount that it applies. Dry spreaders can't be as accurate, but they're going to have several parts. Again, you're going to have the conveyor belt. You're going to have spinners that all can move at different speeds. And as you go across the field, you're going to tell it, I want more or less, so it can speed these up or slow them down. Not as accurate, but better than just applying a blanket rate, particularly if you're looking at, you don't want to overlime some corners and then cause some yield differences there. They can stick around for a while. So this is ours. We just got it so we could do variable rate application of lime and gypsum on research projects, because pH in soils is one of the biggest yield drags, and the more accurate you can make that, you can really even out a field. So this is something I do think that's important. So you have your conveyor belt, speed controls the application rate. The spinner speed is going to control the swath, and that's how you're going to get this out. But you still see, you have to worry about things like particle density. See, you don't really get an even spread across there in terms of nutrient application. So it's only as accurate as you can make it. There are some other things. There is a whole, I don't know how old it is now, because this stuff moves fast. I did a drone talk for Women in Ag. It's on the website, maybe 3 or 4 years ago. I can't remember now, but there's remote and proximal sensor data. I'm not going to get into it deeply because there's plenty in the other lecture that's already out there. But planes in the past, satellites right now, drones, and even handheld tractor mounted. This is one of the easier ones for us to get, obviously, but you can certainly use drones. It's all kinds of sensors, regular RGB, multispectral, thermal, hyperspectral, LiDAR. More than likely, this is what most farmers use, and I can tell you that it works pretty well. Research data, this. Everyday data, this works pretty well. Now, this is the kind of data like on a tractor mounted that they might use in Green Seeker for applying nitrogen. But if you want to map a field, you're all right just using a visual, regular drone like that Phantom 4. So we use them for sensing and mapping. You can see our mapping drone that we have here that we map fields, but there are also drones now that are going to have tanks on them, and they're going to apply herbicides and cover crop seeds, things like that. But you can't cover as much ground, but maybe you can spot spray with it. We're getting down the road towards more people using that. We don't necessarily use them because I figure if you can spray with a tractor, you spray with a four-wheeler like we do, the drone sprayer probably works just fine. University of Georgia is also looking at that. This is what we call proximal sensors or direct contact sensors for mapping soils. We can map our soils with EC meters because soils will conduct electricity. The water will, the organic matter, the texture will. So we have this, what they call a Varus, and we also have something called an EM38. We can go across a field and it also has a pH meter. And besides using your harvest maps, your yield maps, and your soil type maps, we can get a really accurate map of soil type. And what you're actually looking at here, this is the Chesapeake Bay. We're looking at saltwater intrusion coming up as sea levels rising. Across here, we're getting, this is a ditch, and this is salts coming up the ditch. So you can see how instead of guessing where to sample this soil, you can drive across this field in a couple of hours and have an accurate, you want a soil map, but this is a salt map in this case. You can get an accurate map. But water, texture, organic matter, salts, you can't just make a map. You have to sample the soils to figure out, well, why is this low? In this case, I know it's salts, but if this was different, this might be higher clay content through here for whatever's going on. So that's why they call it a parent EC. Map's great, still have to soil sample in that case. Another thing that you can do within precision ag and using GPS is drain tile installation. So here's your, what they call tile is, you see this plastic tubing, but again, here's your GPS unit directly on the tile installation. Here's the correction that they put out in the field itself. So you can make a map ahead of time and say, I'm going to spread my tile. You can see the line there. You can see a line there. And you see a line here. And as it's going across there, it's going to line up. You'll have a map of where you put the drainage tile, and you can place it precisely where you think it's going to do the most benefit. So drain tile installation, not as common, but certainly a benefit to ag. Some of the emerging technologies, because this whole lecture is going to be behind by next year easily and probably useless in 10 years. A lot of self-driving equipment is coming out. Faster than, in some cases, I thought. This is DOT, which was bought by Raven. And then John Deere, you see more and more talk about their autonomous tractors. So self-driving is one thing. You're still sitting in that cab. They're going to have, you can see nobody sitting in here. I don't know the direction this is going to go or what it's going to mean for everybody or the cost or how accurate it's going to be. But this is the direction we're going. Self-driving robots through fields to monitor, to collect grain. I think one of the easiest things they found is a grain cart that can follow you as you're going along, and you don't have an operator in that case. It's one of the first things they have. There's a lot of artificial intelligence going on. So the drones can do this, but one of the things that's taken off very quickly, there's a lot of companies, this is just one I stole this picture from, that have camera sensors mounted now on our booms that are, and we're taking a lot of pictures of weed species so that artificial intelligence can map and monitor and say that's a weed. And instead of blanket applications of pesticide across this field, this camera sees a weed, turns it on. Camera over here sees a weed, turns it on. So one of the things I've seen from one of these companies is they reduced pesticide application by 95% in the field. Now, some of our fields in Delaware, you just need to blanket apply anyway. I've seen that. But going down rows, this is where we're going. And this seems like a very accessible technology. If they get it to work right, something that farmers can adopt easily because it would do all the work for them. But we're just getting into that. But I wouldn't be surprised if in 5 years, if it's a very viable technology. We also have things like electric weeders. It's not necessarily, whoops, crossed right through it. It's not necessarily precision ag technology, but it could be, again, used to, you can map a field and tell it where to weed as you go across there. So that is a summary of stuff that we're either familiar with or we work with. It certainly doesn't include everything. It does not make you any kind of expert in precision ag, but it hopefully gives you some of the terminology so you can discuss with people, or if people talk about this equipment, you can know what parts they're talking about. But you certainly can't be an expert in it. I am not an expert in it. I'm the scientist who helps make application maps, makes decisions on what we needed to do. The engineer in the office next to me, he's the one that calibrates this equipment. He's the one, if I say I want to buy this, he figures out what we need. So you kind of need, when you're talking about when you're talking about precision ag, to me, you need an engineering mind and a science mind, that the agronomy side and then the engineering side to really be accurate in some of the stuff you're looking at. So if you guys have any questions or anything I missed, certainly be right here to answer some of your questions. But you can also email me. There are certainly many more experts within the field that know a lot more than me, and you can look at all the universities across the country that have robust precision ag departments that look at all of this in more detail.
Great, thank you, Jared. I'm going to go ahead at this point and stop the recording, but if anyone has any questions, feel free to add those in the chat pod.